answer it, but my perspective on it is that your question implied that the models had no systematic error. So if you had a situation where where a model couldn't, so there was a systematic bias in your model such that it couldn't get Arctic sea ice and El Nino right at the same time, but there was a tuning parameter in that model which allowed you to get one right or the other. And if the model, I mean, this is an extreme example, but if the model developers implicitly faced that choice, then you would have a situation where a group who was heavily invested in Arctic sea ice would tune their model compensating for the systematic biases in their model such that their Arctic sea ice looked better. Well, of course, but that's ultimately, I mean, that's not necessarily an easy thing to do. Yeah. Anyway, so this is, I'm just going to basically roll on from Reto's talk. There's going to be a lot of connectivity here, so I hope that's okay. But the way I want to frame this is to think about the way that we as a community, as the climate community, as the IPCC, whatever, generally frame the output which we have from ensembles like CMIP, and then look at those approaches and ask what assumptions we're making in the process of doing that. And whether there's any sort of simple approaches we can take to mitigate for those assumptions if they may be problematic. So ultimately, if you're looking at an ensemble like CMIP, you're usually going to be asking some sort of question, and that's usually going to be a question about the future and how it might pan out. So let's imagine that you're interested in looking at heat wave frequency in a particular region of the US, and then you have a modeling, a group of modeling centers who will produce some data for you. You can break down the uncertainty in your assessment of what the heat waves are going to be like in the future in a few different ways, but here's one vaguely sensible way you might do it. So we start off with an uncertainty about what humanity is going to do in the future. Obviously, that comes at the top level of our chain of uncertainty. If the countries of the world radically reduce their greenhouse gas emissions in the next year or the next 10 years, then that's a relevant thing. And then you could say that the second layer of uncertainty is an assessment of global response. So an uncertainty about what the global mean response of the system is going to be, whether we have a climate sensitivity of 6 or whether we have a climate sensitivity of 2 is clearly a first order relevant thing. And then we need a model which hopefully can represent not just the global response, but the regional response. And so work out what local feedbacks might be relevant for representing the global mean temperature rise at a local level. Then you have to worry about the randomness. So simple weather, you need to have enough simulations to sample that. And then finally, you need to be able to relate the results of your model to the thing that you care about, which in this case is the heat wave frequency. So I'm going to look at each of these boxes, but I'm not going to look at them in a necessarily sensible order. So let's do the easy one first. So we can sample emissions by simply taking representative samples of the future. So we have different scenarios which represent different levels of greenhouse gas mitigation which might happen in the future. So we have very extreme scenarios where greenhouse gases are reduced dramatically in the near future, and then a span of scenarios up to those where very little mitigation happens over the course of the century. So comparatively, at least from a physical science perspective, of course, building these scenarios is not a simple thing to do, but from this end of this end of looking at it, this is a simple thing to deal with. We can span that range. Another one which is relatively easy to deal with is the random variability. So if you if you initialize a climate model, the same climate model, and then you make very small perturbations to the initial state of that climate model, and then you run that climate model 20 or 40 times, then you can produce a very well-resolved distribution of the possible future trajectories which that climate model might take due to natural variability alone, so due to the uncertainty in the initial conditions. And there's been a couple of nice studies from this building of building ensembles which sample that uncertainty well, and for some questions this type of uncertainty is really important. If you're looking at trends over a few decades, then this is a type of uncertainty which definitely needs to be sampled. And we certainly need to be able to understand it in the context of the multi-model uncertainty. But fundamentally, this is a thing we can do. This is only limited by computing time. We just need to be able to run the model enough that we've sampled the distribution, and it's fairly clear once you have sampled the distribution. So, but I'm not going to talk about that today because Jen Kay is going to talk about it tomorrow, and there's lots of cool science you can do with that. So I'm not going to stick on that. What I'm going to spend the majority of the time talking about is how we go from global numbers down to regional numbers. And the tools, the best tool, the best archive that we have to do that at the moment is the CMIP archive of climate models. And this is not an experiment which has been designed from the top up. And most of the problems which we will have in analyzing this ensemble stem from that basic problem. So this is a collection of modeling groups, all who have a coordinated experimental design, but their approaches, the complexity of their models, the degree to which they've used components from other models, the things that they care about, all differ, and they don't differ in any organized way, because you're just dealing with different people who care about different things. And so what we need to do is take the output of this model and then reverse it back and so that we can say something objective about the future. But in order to do that, we need to understand the problems. And Reto has very nicely illustrated what a lot of those problems are. So let's firstly look at what is conventionally done with the output of these ensembles. So if you open the last IPCC report, you'll see lots of plots which look something like this. So this is a plot of precipitation change in the future under two different emission scenarios for the future. And what's generally plotted is the multi-model mean response, which is the color, and then where the models tend to agree on the sign or on the intensity, then those reasons are hashed. And so in producing a plot like this, we're making a few assumptions. We're assuming that, firstly, that the multi-model mean is our best estimate. And secondly, we're assuming that if lots of models are coming to the same conclusion, that's a meaningful thing. And we need to question both of those assumptions. So what you could argue is being assumed when we produce a plot like that is that we're assuming a conceptual model of the archive, which is something like this. It's like we're making a lot of measurements of a thing, and the more measurements we make, the more confident we can be on the answer. That's what we're assuming. And so this is what's referred to as the truth and error representation or interpretation of the ensemble. So if this were true, if we had an ensemble which was twice the size of CMIP, we could be twice as confident in the result. And we can talk about whether that is or isn't true. Another interpretation of the ensemble is that the results are indistinguishable, or the model simulations are indistinguishable from truth. And so in that world, we're not necessarily making a measurement of a thing we don't know. What we're doing is we're sampling a distribution. And all we can say is that as we add more and more models to our ensemble, that our knowledge of that distribution improves, but we can't say where reality would be. So the reality doesn't necessarily lie in the center. It could just be one of the models. Or it's equally likely to be any of the models. And the reality And so, okay, so which one of these, if either, is true? So one argument which is put forward for the fact that the truth and error interpretation of the ensemble might hold weight is the fact that the mean, if you take the historical simulations of all of the models in the archive and then you average them together, the mean looks really good. In fact, for each consecutive iteration of CMIP, the multi-model mean has looked considerably better in terms of a root mean square error metric than any of the individual models in the archive. And so some people have used this in the past to defend the idea that the ensemble must be centered on truth, and so that this truth and error interpretation of the archive is an appropriate model to have. And there are two reasons why that might not be the case. And the first one is simple geometry. And so that's literally, if you start off with an ensemble of climate models, so here's your ensemble in the light blue, and then you have the observations in the dark blue here, and then you average all of those models together. Just by geometry, the multi-model mean is likely to lie closer to the observations than the average model. So if you take all the averages of all of these distances and then you compare it to this distance, this is going to look good, and that's just simple geometry. But if you actually look at the ensemble itself, then the situation is even more extreme than that. So that the geometry alone would say that the multi-model mean would look better than the average model. And what you actually have is that the multi-model mean lies closer to the observations than every other model in the archive. And so the mean is still doing exceptionally well, even in the context of this geometrical property of the ensemble that we understand. And in order to understand this, you have to invoke the fact that the models were not developed in a vacuum. So you could argue that the only fair way to produce a model is to lock a physicist in a box with an ecologist and a glaciologist, and then lock them away. Don't let them see the outside world. Don't let them see any observations. Just give them a physics textbook and a biology textbook, and then wait until they've finished and let them out. And in that world, then you could truly use the observations as an independent estimate of how well the model is doing, and you could truly use that to test the projections of the model in the future using the observations of the past. Of course, this is not the case. Of course, every model developer has access to all of the observations before the model even leaves the building. And those observations are used continuously during the tuning process. And this we cannot forget. When we're interpreting the model, when we're interpreting the ensemble that we have, we can't forget that the observations have already been used in the model construction. And so we can explain this. We can explain why the multi-model mean looks so good if we then consider the conceptual idea that each model has been perfectly or effectively perfectly tuned to the observations within the systematic limitations of that model structure. So then you imagine you have one model and you can get it so close to observations, but there's a certain remaining bias because your model representation of the world is imperfect. And then you take another model with different structural biases, and then you tune that, again compensating as best as you can for the systematic biases which remain. And then the residual biases which you would get would then be slightly different. And so then if you throw enough structurally different models into the archive, and then you average them together, all of them with their different structural biases, and average them together, the multi-model mean no longer has that problem. The multi-model mean isn't in itself a physical thing, or a self-consistent physical system. It can cheat, because its structural biases are the average of the structural biases of lots of other different models. And so we can gain this situation. We can produce by construction a multi-model mean which looks more like the observations, because the observations have been used in the tuning of every single climate model. But as Reto pointed out, that doesn't actually tell us anything useful about the future. So let's imagine that our climate model and reality was just a quadratic curve. So, and we have lots of different quadratic curves. You can't see the light blue ones, but let's say we start from an initial ensemble, which is just varying the two parameters of a quadratic curve. And then we have and so we have the red quadratic curve, and this one, let's arbitrarily say, is reality. And then we do a model tuning process, and so we say, okay, we have two observations of reality, one here and one here. And so let's only consider the members of our ensemble which are consistent with that representation of reality. And then let's do that lots of times. So we create lots of situations where we have a collection of ensembles, and we have reality, and we tune the ensembles to look like reality. And what we can do is we can then produce something called a rank histogram. And so that shows how well the ensemble is, or in what way the ensemble is representing the real system. And so what this means is that the rank histogram says, okay, here's our ensemble, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if we went from the bottom to the top, then reality would come at about number 10. And again, because we've tuned the ensemble, reality would come at about number 11 or something. If we ordered the ensemble from top to bottom and counted where the red line came in. Because we've tuned the ensemble in the present day, at the beginning, at the period where we've tuned it, the observations tend to fall in the middle of the ensemble. The ensemble is truth-centered in the period where we've tuned it. But then as we go into the future, because we've only constrained two parameters here, we've only constrained a straight line, and then there's another parameter to the quadratic curve. In the future, that thing that we don't know, third parameter, becomes more and more important. And so as you go into the future, whereas the ensemble was truth-centered here, because we tuned it to be so, in the future, it becomes indistinguishable. So reality could lie anywhere within the sampling space of the ensemble. And so what this means when in the context of the CMIP archive is that the fact that we've tuned all of the models to look like reality in the present day should not give us that much confidence or any confidence on how to interpret the model in the future. And the best case scenario is that the model is indistinguishable from truth. But even that, as we're going to discover, is probably over-optimistic, and for reasons that Reto has pointed out. Okay, so this is the best case scenario. Ensemble members in the future are indistinguishable from truth. One problem and one clear problem, which Reto's mentioned, is that obviously the models are not necessarily equally skillful, but it's really difficult to say which model is best because the answer which you're going to come to depends on the things you're looking at. And I was very happy with just using that as my quote on this matter until this year when Michael asked me to be involved in the National Climate Assessment, and I actually had to say something concrete about it in regards to an actual problem and an actual well-defined set of requirements. And I was very used to passing the buck and saying, well, that will be up to the final researcher to determine what's important for their particular question. Like, oh no, that's me. And so you're left with this very real problem. The models are not equally skillful, and so the way that we've, and this is an ongoing iteration, but the way we're currently thinking about it for the National Climate Assessment is to look at skill metrics over the region which the assessment is focused on. And so in this case, it was North America. And then you take variables which are both related to the things you want to know in the future. So, you want to know about mean state precipitation, but you also want to know statistics about extremes. And if a model is terrible at representing your extremes in the present day, then it's it's not particularly useful to look at that in the future. It's the same as with Reto's Arctic sea ice example. If a model has twice as much sea ice in 2100 as we have today, we can pretty much disregard that. So the same goes for more complex spatial data. If a model like some of these models here, like the Canadian model, is not doing very well on the extremes metrics for North America. So we can't, if that's the thing we care about most, then we can't give that model as high of a weight. But this is arbitrary. I mean, you have to make some judgment calls on this, and this is a difficult thing to do, and it's a difficult thing to defend when it's you who has to defend it. And so the concept of, yeah.
I'm just wondering how you're, like, what are you...
So in this case, these are all these are mean state biases, and in terms of the extremes metrics, and this is not what I want to focus on today, but in terms of the extremes metrics, they're long-term metrics aggregated over several years, like maximum rainfall over a 5-day period, or warmest night, things which can be aggregated over a long time, but nevertheless represent some of the extreme behavior of the model. What this is not representing, and what this is not representing at all, is any variability. And in an explicit sense, and it's not representing trends in an explicit sense. And the methodology which I'm going to outline would need thinking about in the context of looking at short-term trends, because the methodology, as I'm defining it here, is relatively insensitive to initial condition uncertainty. But if we were going to look at 20-year trends, then we couldn't. That would become a very relevant thing to do. So.
And then are these models?
You don't know. You don't know. I mean,
do, right? Most of them. But you use the fact that most likely some of the things. It's some reconstruction. But very few models actually did. On the far right of this metric.
Right.
I'm going to name them, but I will after a beer. But in any case, because that is changing. One of those models.
Mm-hmm.
Jeff, what's up?
I didn't fix this, by the way.
Yeah.
Yeah.
I mean, one point is that heat wave. Looks wrong, then you change the model. All good generation.
Yeah, I mean, one final point. One unfortunate point is that the distances between the models and the differences and the biases of the individual models are greater than the climate change signal over the last 100 years by an order of magnitude. So that's not a first order problem. And it makes interpreting the climate change signal obviously tricky. But, yeah. Yes, that exists, and is there a paper on it? I'm not sure.
I'm not sure about
They just stole the model, so it's okay. So Reto, I'm going to move on. So Reto mentioned emergent constraints, which, and I can't remember where the question came from. I mean, it's a special case. It's a special case of using observations to validate your model, but it's using a sort of it's using a sort of laser focus on a particular process, and sometimes that focus is justified, and sometimes it's not. And so it's become a buzzword over the last few years. Like this is the answer to all problems and constraining processes. I'm not going to comment apart from just 2 words of caution. Lots of people have done it for lots of different processes. First point was the paper by Peter Caldwell last year, demonstrating that you can find basically the degrees of freedom in CMIP and the number of points is sufficiently small that you can get a correlation. You can get a correlation of 0.7 with a random number by total chance. And so, if you found an emergent constraint for a process that you care about, great. But on its own, it means nothing unless you can back it up with a strong physical argument. Because the CMIP archive is 40 models, and then if you then you consider that 20 of those models are effective replicates, the degrees of freedom you have is very small, or is potentially small enough that you can definitely produce correlations by chance. So correlation on its own is not enough. Reto illustrated this problem. You look at the family tree of models, and it's an incestuous mess. It's people and code have been moved from one place to another. And this problem is arguably getting worse, and it's mostly our fault, in this building, NCAR's fault. We feel very happy with ourselves because we have this open source climate model, but then everybody uses that climate model and then modifies, and sometimes they modify a lot, and sometimes they just add some lousy parameterization for something that doesn't matter. So the results that we have are now actually quite highly weighted towards NCAR's projection, and NCAR, maybe we have a good model, but it doesn't deserve the amount of weight that it currently has in the CMIP archive because it's replicated so many times. And so we have to deal with this problem. Yeah.
Can I object in the sense that it's a problem that we think it makes perfectly sense to learn from others? Only a problem if you don't take
I agree.
the interpretation.
I agree. Yes. Please take the CESM source code and play with it, by the way. I'm not trying to...
But you just cannot assume independence when you have results.
That's right. So we need to address this. We can't just ignore it. That's the point. So this is just another way of looking at it. So these are all the cases. light blue lines are where two models share atmospheric code. Green lines is where they share land code. Dark blue lines is where they share some fraction of their ocean code. There's a lot of replication in the archive. We need to deal with this. So given that, are we allowed to produce a plot like that with a hashing saying all of these models agree, therefore we're more confident, when in fact all of those, or some large fraction of those models, have common source code? Just to illustrate the point, if we produce an emergent constraint and we have two models up here, like the NOR-ESM model and CESM BDC, which are in this, for the processes which matter, are the same model, that's going to artificially increase the strength of this correlation, and therefore the emergent constraint which we are justifying on the strength of the correlation is made weaker by the fact, or we could question more because of the fact that there is replication in the ensemble. The good thing is, and Reto's family tree illustrated this, that there is relevant data in the archive itself to actually diagnose this problem and mitigate this problem. So this is a plot of distances. This is a plot of root mean squared differences between every model in the archive and every other model in the archive. And you know, it's complicated, but the thing to notice is it has a lot of structure to it, right? So you can see on the diagonal here, so you know, there's models from the same institution here. So here's the Miroc models here, and these are dark blues. These are all close to each other. Here's the Hadley Center models here. Here's the GFDL models and the NCAR models. You know, they all form these little blue triangles on the diagonal. And then you have some models which are like dark red all the way. And these models are like far away from the whole ensemble in every sense. They're far away from every other model in the ensemble. And so this is useful information. And we can use that information to produce a family tree, like Reto showed. And we can also use it to produce something quantitative, to produce a weighting scheme. And so let's imagine that we were evaluating the ensemble on two observables. So these are two things where the models are producing something, and then we know what the observations are. So objectively, we can look at this and we can say, okay, well, we've got how many models? 7 models. These ones look quite good, but they look suspiciously close together. These 3 are quite poor, also suspiciously close together. And this one is all right. This one probably looks rough. So how can we take that sort of subjective evaluation and then turn it into something turn it into something concrete? So the easier thing to do, and the thing we've been doing for decades or trying to do for decades, is look at how models perform in terms of their skill. So, and this is usually in some way, a complicated way or a simple way, simply looking at the distance between the models and the observations for the observables that we have, which we've determined are relevant for the processes which we're trying to investigate. And so that involves making some sort of judgment call, making some judgment call about how far away from the observations you're happy for that model to be for you to still take it into account in your analysis. And there are a couple of ways you could do this. So you could propose a weighting scheme which looked like a Gaussian, and then you could adjust the width of that Gaussian until you got your best fitting skill score for reproducing your observations. That might be one way you might think about it. You could justify others, I'm sure, depending on the question that you're answering. The second question is this question of model independence. And we can start thinking about this in a quantitative way by asking the following question: how close can a model be to another model before it looks suspicious? Right? But there are ways which we can quantify that, and it roughly comes down to evaluating a length scale, right? So it involves working out how close one model can be to another before we should effectively call them the same model. It's implausible that those two models could have lied so close in this space without them sharing some ancestry, some common code. But the data, again, can provide us with that length scale. So this is a histogram of all of the distances between all of the models in the archive. So if we go back to that grid plot I showed you a minute ago, this is a histogram of all of those distances. So we can think about how close two models need to be before it's suspicious in two ways. One is to, and this is the black curve here, is to assume if we had a purely random set of models which were allowed to vary with the same number of degrees of freedom which we considered for making this distance metric, then we allowed that those ensembles to be a multivariate normal distribution and sampled that hundreds of times, we get the black curve. And so that would make us questionable about these models here, which lie closer together than you would ever get by chance. The other way we can do it, and the simpler way we can do it, is to simply take a large ensemble. So to take a large initial condition ensemble of models which come from the same institution. Is that your time limit? Okay. And so that's the yellow bar here. And so that says that if there's no structural difference between the model, between two models, because the only thing which is changing is the initial conditions, then that gives us a length scale by looking at the distances between the models in that initial condition ensemble. The thing to note here is in terms of mean states, there is orders of magnitude difference between the average distance between models in CMIP and the average distance between models in the large ensemble. For the purposes of mean state evaluation, these are identical. For the purposes of a short-term trend, they are not. But in terms of the mean state, they are absolutely identical and clearly distinguished from every other model in the archive, in the CMIP archive. But this gives us a length scale. So this says if two models in the archive come close to that distance, then we can effectively, we should downweight them because they are more similar than we could expect by chance alone. So by combining those two things together, we can get an overall weight. We can write this down as an equation, which I don't think I'm going to describe now, but if you want to come talk to me afterwards, do. But it involves basically just establishing two parameters. This parameter here is the degree to which this is how close you allow two models to be before you consider them to be the same, and this parameter here is how bad does a model have to be before you want to throw it out. And so this, in a broad sense, allows you to weight models for their quality and their independence, and you end up with this trade-off. So the models which are doing better, the models with a better overall score, tend to be those ones which are also replicated most in the ensemble. And so this is something we would suspect just by looking at the original ensemble and knowing where code has been used more than once. And it also has the sort of slightly roundabout property that applying both the original because the better models have been replicated, we're already applying a quality weighting to the ensemble when we're looking at it. And it's not perfect, but there's a general tendency for that to happen. But we can do that in a more objective sense. And if you want to talk to me about that afterwards, I'd be happy to go through it. So very finally, briefly, I want to talk about what CMIP doesn't do. So I've left this to last. When we look at the distribution of climate sensitivity, which you get from the CMIP archive, it is narrower than the outer tails of the distribution of what climate sensitivity might purely be from an observational sense. And irrespective of how we try to constrain climate sensitivity, the highest sensitivity model that we have in CMIP doesn't necessarily sample, explicitly doesn't sample the tails of this distribution. And so when we are making an inference that the distribution that we get from CMIP is is representative of the probability of futures which we might get, that is false. What we have is a collection of best guesses. And that's because every single model in the archive has to make some judgment calls about how to represent processes which exist on the subgrid scale. And because of the way that our community works at the moment, and because of the limitations that we have and the resources that we have, each center broadly only produces one version of their model. They produce the most likely version of their model. And so on the few occasions where groups have sampled all of the parameters or a lot of the parameters associated with their convection, with their clouds, with their vegetation, they've found that you can get a climate sensitivity, that this climate sensitivity can vary significantly as a function of those parameters. And in a single model, you can get a global mean temperature rise which falls outside of the CMIP range. This is just something to keep in your head when you're making a conclusion based on CMIP. So we can do this with a single model. We can get a wide range of results, but you also can't. The PPEs aren't the only answer because they haven't been looked at. So you do get a wide range. So you perturb all the parameters in your model, and then you get some models which are potentially crazy, which look nothing like Earth. And then so you need a system for dealing with that. You do sample the tails of the distribution of global response, but then you also have a problem that most of the models in your archive, or most of the models in a perturbed physics ensemble, end up looking like the default model because some of the parameters don't do anything. And so unless you've dealt with all of those things, you can't necessarily use a perturbed physics ensemble to evaluate uncertainty about the future. And furthermore, people who've looked at this have found that the CMIP archive is representing a greater structural diversity than you can ever get by perturbing parameters in a single model. And so what this plot broadly shows is if you look at CMIP, and if you look at a perturbed physics ensemble, and then you look at a lot of different observations and where the observations fall with respect to the ensemble, then if you look at a PPE, then the observations always tend to come on one side, or usually tend to come on one side or the other side of the whole ensemble. So the whole ensemble is clustered together, usually, and then the observations are up here. And if you look at CMIP, then you get a much broader distribution. So if you look at enough observations, then broadly the observations look like they're a member of the ensemble for the past, with all the caveats that we have earlier in the talk. Okay, that's it. Sorry. Here are my conclusions.